Welcome back to part 2 of Dave Does Math from Home video on flux integrals, section 17.6. I have what I think is a pretty nice looking flux integral here. I want to start relatively simple, relatively calm with, we're going to just look at a flat horizontal plane. We're going to parameterize this. The parameterization of this plane is already given. The parameterization is x, y, and 3. That we have a constant here for z is what makes this thing flat and horizontal. Z is not changing anywhere. Z is just 3. We have a x can do its x thing, y can do its y thing, but we're flat. We're horizontal. Z is always 3. So this is a flat horizontal plane. It's about this big. It's about 8 units big. X varies between 0 and 2. Y varies between 0 and 4. The vector space is a little crazy. Vector space is e to the y sine x and z squared, but hopefully the simplicity of the surface we're looking at this thing through will be nice. So we're just going to start with step 1. Step 1 is actually already given to us. I'm just going to write it down anyway. S equals x, y, 3, and 0 is less than or equal to x, less than or equal to 2, 0 less than or equal to y, less than or equal to 4. It probably seems a little bit silly that I wrote this over here and then I just rewrote it here. I want to sort of get into the habit of writing down this as step 1 because you don't have this written already. So, or maybe you do. Maybe you're diligently copying all this down. But in homework problems, even if they tell you what the surface is, just make sure that you write that down first. In step 2, I need to find the derivative with respect to x, and that should be 1, 0, 0. And I need to find the derivative with respect to y, and that'll be 0, 1, 0. So very nice, simple, straightforward derivatives. I need to get my normal vector. I need the cross product of these two partials. So sx cross xy, that will give me cross products. I, j, k, 1, 0, 0, 0, 1, 0. Determinant of this should be, when I expand along I, I'm going to get 0 minus 0, so I'll have 0i. When I expand across j, I'll get 0 minus 0, so 0j. And when I expand across k, I will get 1 minus 0, so I have 1k. So written with brackets, my normal vector is 0, 0, 1. And there's two things you should do once you have n, two little like stop and check to make sure this makes sense moments. You should ask yourself, are these vectors I have, are they perpendicular to my surface? This surface I described as a flat horizontal plane. These vectors point straight up. So yeah, I would say that it should be pretty intuitive that these vectors that point up everywhere are perpendicular to this flat plane. The other thing you need to check is the orientation. Cross products are not commutative. If you do sx cross xy, you will get a different answer than if you do sy cross sx. The answer we got points up. If we did it the other way, the vector would point down. So you have to make sure that it kind of doesn't matter which way you do it in terms of like what these values are, but you need to make sure that they match the orientation. If you do it the wrong way and the orientation doesn't match, don't do it again. Just make everything negative. And then the orientation will match and you'll be all set. So here, this vector points up. We wanted vectors pointing up, so we're all set. The orientation matches. And that's it. That's our end. We are already finished with step 2, and we have thought about it, and our answer makes sense so far. So we can move to step 3. I'm about to run out of room. I might need to erase some of this before I'm done. Step 3 is we need to express f in terms of x and y. The good news that x is already in terms of x and y's mostly. This is the thing that's going to have to change. In our parameterization, x is x, and that doesn't have to change. We're good. Y is y. That doesn't have to change, and we're good. In our parameterization, z is 3. So this thing has to change. So f expressed in terms of this parameterization is going to look like e to the y sine x 9. Instead of z squared, we're going to use 3. And we'll just get 9 all the time, every time. So this is my f. Next thing I need to do is I need to find the dot product of f and n. I don't know why I have equal signs here. F dot n is going to be 0, nice, plus 0, also nice, plus 9, which is just 9. So that's convenient. So in step 5, I'll come over here to do step 5. In step 5, we need to do the double integral of this thing. So I need to set up the double integral. F dot n is 9, so I'm integrating 9. I'm doing it with respect to these two variables. So I need a dx and a dy. And I need to use these bounds on these variables. X goes from 0 to 2, and y goes from 0 to 4. Here's the good news. If you're really, really dreading the part where we do double integrals and you don't want to deal with that and you hate it and you wish it would go away, good news is this. If you're integrating a constant over an area, you can just multiply the constant by this area. So if you do this integral out, which you are welcome to verify on your own if you like, if you do this integral out, you're going to multiply the 9 by 2, and then you're going to multiply by 4. Or you could just say 9 is sort of like effectively, if you think back to volumes, if you have a constant height of 9, and the area here is a rectangle with length and width 2 and 4, then you should end up with 72 as your grand total flux integral. And the book will talk about this a little bit as well. If you click the help me solve this or show me an example button, the book will talk about how you're sort of transforming this flux integral into more of an area integral. And when you get constants here, you can multiply your constants by whatever area you have here to get your final result. And we get 72. That's our first flux integral. We finished that in less than 9 minutes. We are doing great. Let's do another one that's a little more exciting. I want to do a flux integral on another plane, but I want it to be a more interesting plane. I want to use the sort of like the tetrahedron shaped surface of the plane that we did a couple versions of the volume of in chapter 16. So I'm going to erase all this. I'll grab a new marker because this black one feels like it's fading a little bit at the end there. Here we go. So I want to take a look at the surface. Z equals, let's do 6 minus x minus 3y in first octant. And I want to do f vector space. I want to start out with a very simple vector space here, and then I want to do like the same problem with a much more interesting vector space so we can see how that changes things. So I'm going to start out with the first vector space I'm going to use is I like to call this one like the rainfall vector space. So if we're doing rainfall, I guess this isn't true when wind gets involved, but let's imagine that usually there's no wind and rain is just falling straight down. If rain is falling straight down, then your vector space looks like this. So we're going to do the rainfall vector space. Everything is going down all the time, straight down. No x's, no y's. No, it doesn't even depend on z. It's just in the direction of z. And we want this surface. So we'll start out with parameterizing the surface. S equals, this is another one. We have x's and y's. Let's just use x's and y's. The surface is going to be x for x, y for y, and 6 minus x minus 3y for z. This is my parameterization. The bounds on this one are going to get a little bit weird because one of the bounds isn't a constant. One of the bounds is sort of like a diagonal line. If you imagine this thing, this has an x-intercept of 6, has a y-intercept of 2. So the bounds on this are going to be this diagonal line. So if we're going to integrate on x first, x goes from 0 to this line, and this line is, do I want to integrate on x first? Yeah. 6 minus 3y. That's what x equals. X is 6 minus 3y. So it's going to feel a little weird using variables as some of your bounds here, but it follows all of the same rules as double and triple integrals when we did those in chapter 16. So 0 is less than or equal to x is less than or equal to 6 minus 3y. If we're doing this, we're sort of committing to integrating along x first, and then y is going to go from 0 to 2, which is fine. This is if we want to do the double integral version. Okay, no, I'll talk about that when we get there. Never mind. Okay, so I have my parameterized surface. I have the bounds, even though one of them is a little weird looking. And I'm going to now go to step 2, where I take derivatives. Derivative with respect to x is 1, 0, negative 1. Derivative with respect to y is going to be 0, 1, negative 3. And the normal vector is going to be their cross product. So cross product is going to be I, j, k, 1, 0, negative. Oh, I need to do an orientation. Let's have this thing oriented up. Okay. 0, 1, negative 3. I'm not sure if this x and then y is the correct order to make this thing oriented up, but again, if we guess wrong, we're not going to do it again. We're just going to make n negative. We're going to flip it upside down, and then it'll be oriented up, and we'll be all set. So this cross product is going to give me, when I expand across I, it's going to give me 0 minus negative 1, so 1i. When I expand across j, it's going to give me negative 3 minus 0, but j is the one that's all starts negative, so it'll be positive 3, 3j. And when I expand across k, it'll give me 1 minus 0, so plus k. So as a bracketed vector, it'll be 1, 3, 1. This is the normal vector. All right. Step 3 is where we need to express f in terms of these variables. The good news for us here is that f has no variables. F is just zeros and a negative 1, so when we swap the variables around, nothing changes because there are no variables to swap. So that'll stay 0, 0, negative 1. And then we need a dot product. dot product of f and n is -1. And then we'll integrate that. We need a double integral. I should not be writing this down here. Let's come over here. Step 5. We need to do a double integral. The function we're integrating is -1. We're going to do dx and then dy because we have the bounds on x as our variable. So x is going to go from 0 to 6 minus 3y. Y is going to go from 0 to 2. That's all well and good. Once again, we're in the situation where we could do this whole double integral out if you wanted to, and that's totally fine. I think it's very possible to do this. We could also, we're in the situation where we're integrating a constant over an area. So when we integrate the constant over an area, we can just multiply them together. The constant times the area of this space. So this space is a triangle with area 1/2 base times height, which is 1/2 times 6 times 2, which is 6. So you could just say that this whole thing is -6 if you wanted to, or again, you could do the integral. I've done the integral, it's -6. So, first example had a wild-looking vector field, like e to the y's and sine x's, and it came out really nice because we were using a very simple surface, where the normal vectors only cared about k, and a lot of the stuff disappeared when we took the dot product. Here we used a more interesting surface. We have one of these tetrahedron planes that's coming down in the first octant. So we had a much more interesting surface that let us showcase the fun of taking a cross product. And then we multiplied that by a really, really simple vector field. And we again got this. Steps 3, 4, and 5 were very simple because of that. So next up on our list is I want to do an example where we have a moderately interesting vector field and a moderately interesting surface. And to ease us into that, I want to use the same surface. I'm going to use the same z equals 6 minus x minus 3y thing. I just want to use a different vector space now. So I'm going to erase part of this. I definitely can erase all of this. And that stays because that's just a surface. Steps 3, 4, and 5 can go. And this vector field can go to be replaced by something more interesting. The more interesting thing I want to replace this with is sort of the rotational vector field. So I want to use a marker that functions. Leave that one sitting upside down for a while. Hopefully it behaves better. Let's just use a different color so I can talk about what's different now. Let's do -y, x, and 1. So this is almost like a spiral vector field. The -x, y, that's our standard like toilet flush rotational vector field. That there's always a +1 attached to that means it's going to spiral just at a constant upward lift of 1. And I want to see what happens when this vector field that spirals with a constant upward lift of 1 flows through our triangular tetrahedron plane nestled against the origin. So we need to start over again with step 3, where we're expressing f in terms of x and y. F is already in terms of f and y. If there was a z in here somewhere, we would need to replace that z with this function here. But we don't have the z's in there, so we're all set. F is not going to change. It's just -y, x, 1. But now I need a dot product. F dot n is going to be -y plus 3x plus 1. So now this is the function that I need to hit with a double integral. Double integral of 3x minus y plus 1 dx dy. And we already have our bounds on x, 0 to 6 minus 3y, and our bounds on y are going to be 0 to 2. This puts us in a situation where we can't just use the area trick, where we have a constant here and we multiply by the area here and we get our answer easily. So for this one, we would have to do the double integral, and we would get integral from 0 to 2. X is first. This will be 3 halves x squared minus yx plus x, evaluated from 0 to 6 minus 3y dy. From here, everything falls out normally just like a regular double integral would. There's no surprises. There's no weird shenanigans. You substitute this in for all your x's. You do a lot of algebra. You integrate a second time with respect to y. You plug in 0 and 2. We all know how to do that. We've all been through chapter 16. This video is 21 minutes long. I'm going to cut it here. If you want to finish this, let me know what the answer is. If you don't want to finish this, that's okay. I'll forget that it's in this video in like 20 minutes, so no pressure. Stay tuned for more examples. There's more coming.